In the last class, we have discussed in detail about boragine or borazole, which is called as inorganic benzene. There we have studied preparation, properties and structure of borazole. And finally, we came to know that borazine is also called as a inorganic benzene. Hence, borazine shows a isoelectronic structure as that of benzene, where all the 6 carbon atoms of benzene are replaced by 3 boron atoms and 3 nitrogen atoms. So today I am going to discuss about the second compound of boron, that is diborane, B2H6. Boron may also exhibits many of the compounds like boron trifluoride, BF3, boragine, that is B3N3H6, as we have already completed in the last class, boron nitride, that is Bn, and boric acid H3BO3. None of the elements belonging to third A group directly reacts with hydrogen, but a number of interesting hydrides are known. The formation of boron hydride by the action of acid and magnesium boride has been known for a long time. The study of boranes was made by Stock and his co-workers, and they shown that the boron forms a chain compound with hydrogen. Hence, there exists a series of volatile boron hydrides as follows, that is diborane H2B2H6, tetraborane B4H10, pentaborane B5H9, hexaborane B7H10, etc. Similarly, octa, nona, decaboranes are also known. The boron hydrides have been further divided into 2 types. Actually, there are 4 types, but for our limit or our class, only 2 types of hydrides, that is boranes and hydroboranes, is to be studied. Generally, boranes are represented by the general formula BnHn plus 4. Boranes are represented by the formula BnHn plus 4. For example, B2H6, B5H11, B6H12, etc. Coming to the second type of compounds, that is hydroboranes. As boranes are divided into 2 types, that is boranes and hydroboranes. Boranes are represented by the formula BnHn plus 4, whereas hydroboranes are represented by the general formula BnHn plus 6. BnHn plus 6 is the general formula for the hydroboranes. Now coming to the what are boranes are hydroboranes. Boron hydrides are electron deficient compounds in which there are no sufficient electrons available to bond all the atoms in a molecule together by a normal covalent bond. What are boranes or hydroborane? Means boron hydrides are the electron deficient compounds in which there are no sufficient number of electrons were available to bind or bond all the atoms in a molecule together by a normal covalent bond. That is, as an example, B4H10, B5H11, B6H12, that is a tetraborane, pentaborane, hexaborane, etc. Coming to the diborane B2H6. This is the second compound to be studied. First of all, we have to see the methods of preparation of diborane. In the first method, diborane can be obtained in a large scale by mixing a etherical solution of lithium aluminium hydride, a etherical solution of LiAlH4 and boron trichloride, that is BCl3, in ether through a current of dry nitrogen. The preparation reaction of diborane can be represented as 3 moles of lithium aluminium hydride reacting with 4 moles of boron trichloride. Both the reactants are going to be preferably taken in a etherical media, and the total media is maintained under ether only. So here, when we react 3 moles of lithium aluminium hydride with 4 moles of boron trichloride, we may get 3 moles of lithium chloride, 3 moles of aluminium chloride, along with the formation of 2 moles of diborane, that is B2H6. So this is the first method of preparing diborane, where lithium aluminium hydride and boron trichlorides are taken in a etherical media through a current of dihydrogen. Diborane is obtained. Coming to the second method of preparation of diborane. Diborane can also be prepared by reacting boron trifluoride with 3 moles of 6 moles of lithium hydride, that is 2BF3, reacting with 6 moles of lithium hydride. It gives 1 mole of diborane with the formation of 6 mole of lithium fluoride. In the second method, diborane can also be obtained by the action of boron trifluoride in a etherical media along with lithium hydride or sodium hydride. Both the reactants are taken in a etherical media. So we are going to obtain 1 mole of diborane, and also there is a formation of 6 moles of sodium fluoride if you have taken sodium hydride as a reactant, or 6 moles of lithium fluoride if you have taken lithium hydride as one of the reactant. So this is the second method of preparing diborane. Hmm. Coming to the important aspect in the diborane, that is structure of diborane. As we know, diborane is an electron deficient compound in which there are no enough bonding electrons are available to join all the atoms in the molecule together by a normal covalent bond. So to deal with the structure of diborane, we have to consider the atomic number and electronic configuration of boron in the ground state as well as in the excited state. That is, the atomic number of boron is 5. Its configuration is 1s2, 2s2, 2p1. 1s2, 2s2, 2p1 is the electronic configuration of boron as its atomic number is 5. The valence shell configuration of boron is represented as 2s2, 2p1. Diagrammatically, the electronic configuration of boron atom under ground state is represented as 1s2, 2s2, 2p1 is the general configuration, whereas the ground state configuration under the valence shell of boron is 2s2 and 2p1. This is the ground state configuration. In ground state, this is the ground state configuration of boron atom under the valence shell. Coming to the excited state of boron atom. In the excited state, one electron of boron from 2s subshell is excited to 2py subshell as 2py1. So here in the first excited state, as an electron belonging to 2s subshell is excited to 2py level, here it indicates 3 half-filled atomic orbitals which are available for bonding. In the ground state, as the configuration is 2s2 and 2p1, there is only one half-filled atomic orbital or unpaired electron is available, which can make only one bond with one hydrogen atom. But in diborane, one boron atom is linked with 3 hydrogen atom. That's why we have to consider the excited state configuration of boron. That is, boron atom is taken in the first excited state. In the first excited state, an electron belonging to 1s subshell is excited to 2py subshell, indicating 3 half-filled atomic orbitals or 3 unpaired electrons which can make a bond with 3 different hydrogen atom. That is, one boron atom under the first excited state is having 3 unpaired electrons or 3 half-filled atomic orbitals which can bind with 3 electrons of hydrogen, making 3 BH3 bonds. Here in the first excited state, we are going to observe 3 unpaired electrons as I have explained already. These 3 unpaired electrons may combine with 3 hydrogen atoms as shown below in figure 192. Here, each boron atom can link itself to 3 hydrogen atom. Here, each boron atom can link itself to 3 hydrogen atoms as shown in figure 1 and in figure 2. In figure 1, one boron atom having 3 unpaired electrons is binding with 3 hydrogen atom having 1 electron each, and in the second figure one more boron atom is binding with another 3 hydrogen atom having 3 unpaired electron, 1 in each hydrogen atom. So here 2 boron atoms can link to 6 hydrogen atoms. Thus, each boron atom can link itself to 3 hydrogen atom and there are no electron left to form a bond between 2 boron atoms. In this diagram, each boron atom can link itself to 3 hydrogen atoms and there are no electron left to form a bond between 2 boron atoms. There exists a question mark how both the boron atom can bind together to form a diborane molecule. Here we have taken 2 different BH3 units. One boron atom with 3 electron is linked with 3 hydrogen atom and another boron atom having 3 electrons is linked with another 3 hydrogen atom having 1 electron each. In order to understand how 2 electrons can bind 3 atoms together, for this we may consider separately the 2 BH2 units or fragments and the bridging hydrogen atoms. That is, 2 different BH2 fragments and a bridging hydrogen atoms. Evidently, there is one lone electron around each boron atom. This electron pulls the orbitary electron around the hydrogen and these 2 electrons visit both the boron atoms and hydrogen nucleus and there establish a BHB bridge. Electron diffraction and infrared spectroscopic experiment has shown that the structure of diborane is as follows. The various bond distance and bond angles are as shown in the figure. The following structure indicates the structure of diborane, where boron atoms, that is 2 boron atoms are linked with 6 hydrogen atoms. Here, out of 6 hydrogen atom, the 4 hydrogen atoms, that is 2 on the left side and 2 on the right side, are known as terminal hydrogen atoms and are different in environment from other 2 hydrogen atoms, which are known as bridging hydrogen atoms. The 2 boron atoms and 4 terminal hydrogen atoms. 2 boron atoms and 4 terminal hydrogen atoms are lie in the same plane, while the 2 bridging hydrogen atoms, one above and one below, lie perpendicular to the plane of boron atom and terminal hydrogen atom. The various bond distance and bond angles are as shown in the figure. Here, the bond distance between BH2, that is 1 boron atom and terminal hydrogen atom, is 120 degree, whereas the bond angle between boron atom is 97 degree. The bond angle between bridging hydrogen atom is 83 degree, whereas the bond distance between boron and terminal hydrogen is 1.19 Armstrong, and the bond distance between boron and bridging hydrogen atom is 1.31 Armstrong units. Once again, in the diagram, it can be explained as both boron atoms and 4 terminal hydrogen atoms are lie in the same plane, whereas the bridging hydrogen atoms are lie perpendicular to the plane, and the various bond distance and bond angles are as shown. The 4 hydrogen atoms, that is 2 on the left side and 2 on the right side, are known as terminal hydrogen and are different in environment from the 2 hydrogen atoms, which are known as bridging hydrogen atoms. The 2 boron atoms and 4 terminal hydrogen atoms lie in the same plane, while the 2 bridging hydrogen atoms, one above and one below, lie perpendicular to the plane of boron atom and terminal hydrogen atom. Coming to the last step of diborane, that is uses. Diborane is used as a rocket fuel for supersonic bombers. It is used for the preparation of higher energy fuels and propellant, for preparing higher boranes. Diborane is also used as a reducing agent, and also it is used as a catalyst in polymerization for welding torches. Thank you.